Welcome to the abstract algebra lesson on groups concerning basic theorems and subgroups. Our first theorem is fairly simple. The reason I put it here is to illustrate some of the definitions or the properties of a group. So we have if A times A, so this is star is a group operation, equals A in a group G with operation star or asterisk, then A is the identity element. So we do is we apply the inverse. Since we know we have a group, we know the inverse exists for A, and we apply that to both sides. And recall that the inverse was defined to be on the left. So we multiply on the left here, this equation here multiplied on the left by the inverse. Then we work on each side here. On the right side, this is by definition the identity, and then on the left side we use the associative law to group the first two terms together, and then have the third term just separately here. Then we apply the identity here, so this is the identity, and then you get this here, the identity times A equals the identity, and then finally apply the identity property to the left side of the equation here, and we just get A equals E, which is the identity. So that's what we wanted to show. Recall from the definition of a group that we had the identity times A equals A, but not the other way around. We didn't have A times the identity equals A, but we can prove that. We had the same issue or a similar issue with the inverse. It was defined to be on the left, so A inverse times A equals the identity, but we could also prove that A times A inverse equals the identity, which is what we have in this theorem. So this theorem holds whether you have an abelian group or not. It's always true. Of course, if you have an abelian group, then there's nothing in addition to prove because you have commutativity. But as I say, if you don't have if your group in general is not commutative, you do have to have these two things holding true. So let's prove those. We'll take this one first. We'll multiply both sides of this by A. Get this here. Then we'll use the associative law to group the first two terms together and then have A here. We'll leave this side alone. Then we multiply both sides of this by A inverse. So we get this on the left. Then on the right we have this here. And then of course E times the identity times A inverse is just the element itself, which would be A inverse. And you notice we have the same term here, here, and here. And we proved in theorem 2 that if you have an element of the group times itself equaling that same element of the group, that has to be the identity. So that means that this thing here, A times A inverse equals the identity, which is what we wanted to prove. Then the second part is even easier because we can make use of this here. So we have A times the identity, and then we know that the identity equals, from here, A inverse times A. Then we use the associative law to group these first two together. Then we use this first part of the theorem that we just proved, and we know this is the identity. Then we use the definition of identity here, and we get A. So A times the identity equals A, and we've proven the second part of the theorem. In the following theorem, we show that the identity element is unique for a given group, and that there is only one inverse for each element of a group. So just what I said here, we've stated it a little bit more precisely. For a group G with operation star, the following statements hold true. If F, an element of G, satisfies this here, F times A equals A for every A, then F is the identity. For a given element of group G, element A, if B times A equals the identity, then B is the inverse of A. So the first part of the theorem, we'll prove that here. The given condition, F times A equals A for every A in G. So we can take A equals F, and that gives us F times F equals F. But then by theorem 2, F has to equal the identity. So that proves the first part. For the second part, we'll use theorem 3 and the associative law. So we'll start with B, and we know that equals B times the identity for any element B in our group. And then we can, from theorem 3, we have the identity equals A times A inverse. So we have this here. Then we use the associative law, so we group B and A together. And then we have A inverse here. But then we know that we're given that B times A equals the identity. So we have the identity times A inverse, and the identity times anything is the element itself, and you get A inverse. And so we have, following this string of equalities, we have B equals A inverse, which is what we wanted to prove. We have yet another basics theorem on this slide. These are properties you would be familiar with from high school algebra. The difference here is they apply to any group, whether they be matrices or modular integers, and several of the other examples that we saw. So the first one is the cancellation law. So if you have x times A equals x times B, or flipping the order here, A times X equals B times X, then you can just cancel the X out and get A equals B. Then the inverse of the inverse equals the element itself. And then the inverse of a product of elements is the inverse of the elements, and it's in reverse order here. So let's prove each one of these. First one is we have, and we'll just prove the first part because the second part is almost the same proof. So we have, we start with A, that equals the identity times A. Then the identity equals X inverse times X times A. Then we use the associative rule to combine the X and the A and have the X inverse separately here. And then we're given that X times A equals X times B. So that gets us from here to here. Then we use the associative law again to combine these two together. We have this. Then X inverse times X is the identity, and the identity times B is B. So A equals B in this first case. And the second case, as I say, is almost the same. Then in the second one, by theorem 4, part 2, inverses are unique. So the inverse of A inverse is the unique inverse of A inverse, i.e., the inverse of A inverse is the unique element of G such that this holds true. But by theorem 3, we also have that A times A inverse equals the identity. So we have two different things multiplied times A inverse giving us the identity, which means that A has to equal the inverse of A inverse. That's by uniqueness. So that's what we have here, and that's what we wanted to prove. Then the third one, we'll prove it for just n equals 2, and we'll take, rather than using these subscripts, we'll just use A and B. And then it'll follow from mathematical induction that this holds for n elements, where n is greater than 2. Okay, so we have A times B inverse times A inverse. And then we use the associative rule here to combine these two middle ones together. And then this is the identity. So we have A times the identity times A inverse. Then A times the identity, of course, is just A. and then A times A inverse is the identity. So what we've shown is that this times this gives us the identity, which means this term here is the inverse of this product. So that proves the theorem in case n equals 2. And as I say, the general result just follows by mathematical induction. I have a couple of unrelated topics here on this slide. The first one is a remark. You may be wondering why we didn't just take as part of the definition of a group some of the things we've proven in the last few slides. And the idea in general, not for group theory, but in general, is to have as few axioms and assumptions and definitions as possible, and then prove your results from that very minimum set of axioms. So that was the reason for not making these results in the past few slides as part of the definition of a group. It's a general goal in mathematics. You may have seen that in geometry, where the idea is to have a very minimum number of axioms to then prove your theorems from those. And when you may get stuck at some point where you just can't prove another result, and you may need another axiom, in which case that's a valid thing to do. The second point, unrelated, is concerning associativity. You have a string of operations like we have here. Parentheses are not needed. One can group the terms in any manner, and the result will be the same. So this is known as generalized associativity. And for a proof of this, you can see the theorem 2.49 in the book by Rothman. I referenced this book in my first lesson on groups. I'll give you the reference again and the link to this. I believe you can borrow this book from the Internet Archive without having to buy it. So if you're interested in the proof, I'll give you a reference on that. We can define exponentiation for groups in a very similar manner that we've done in high school algebra. But the difference here is it applies to any group. So if you have an element A in a group G, the nth power of A is written out like this. This is really just notation. It's just A repeated n times, and the grouping doesn't matter because of what we said in the previous slide concerning the associative law. Then A to the m plus n is A to the m times A to the n. That just follows from the definition here. In a similar manner, we have A to the m to the n is A to the m times n. That follows from this definition also. If A and B commute, then AB to the n equals A to the n times B to the n. This is not always true. For example, if you have matrices, a group of matrices, this isn't necessarily true. If we use an alternate notation for the inverse of A written this way here, rather than our other notation, then we can write some formulas related to the powers here. So this is kind of making the case for using this notation as opposed to this notation. Just give you an example. And again, this is what you would be familiar with from high school algebra, but it holds in this more general setting. So A to the minus 3, using our definition of exponentiation, is A inverse times A inverse times A inverse squared. And then that would just be A inverse times itself 6 times. And we would write that as A to the minus 6. So it's just multiplying the 2 times the minus 3. So in other words, these things hold, these properties hold even for inverses. When talking about groups and exponents, it is more natural to use the alternate notation. Yeah, I just made that point here. And we would use 1 instead of E for the identity. So for example, it's kind of natural to say A times A inverse equals A to the 0, which is 1. So you'll see me using this notation, and you'll see this in papers and books. The order of an element, A, in a group is defined to be the smallest integer such that A to the that integer power is the identity one. As the name suggests, a subgroup H of a group G, written this way here, is a subset of G that fulfills the group axioms. And we already saw this in the previous lecture when I talked about the alternating group of the symmetric group Sn, the alternating group A sub n. So I've already used the term before, but I'm formally defining it here. A group always has at least two trivial subgroups, the group itself and the subgroup consisting only of the identity element. Not very interesting, but it's important to note this with regard to some proofs. As I just mentioned, we've already seen this. For example, the A sub n is a subgroup of the symmetric group. Another example, consider the group under addition of the modular numbers under 8. Powers of 3, which generate the set 1 and 3, form a subgroup. Also the powers of 5, which generate the elements 1 and 5. I'll leave that for you to check, that taking the different powers mod 8, you just get 1 and 3 and 1 and 5. But those are both subgroups. So we have a couple of examples of actually 3 examples of non-trivial subgroups of a group. And on the next slide, I'll give you a theorem that'll help identify when a subset is a subgroup of a group. Theorem 6 gives us another way of showing that a subset of a group is a subgroup. It reads as follows: a subset H of a group G is a subgroup if and only if H is non-empty, and whenever X and Y are elements of H, then X times Y inverse is an element of H. So this is if and only if. We need to prove it in 2 directions, forward and backwards. First, assume H is a subgroup of G, and X and Y are an element of H. Then, since H is a group in and of itself, we know that Y inverse is an element of H. And then by the closure property, which applies to H as a group, we have X times Y inverse is an element of H. So that gives us this part of the theorem. And again, since H is a group in and of itself, that means the identity is an element of H, thus H is non-empty. So going in that direction was easy. Going in the other direction is a little bit harder, or it takes a little bit longer to explain. Going in the other direction, assume X and Y are an element of H, implies that X times Y inverse is an element of H and that H is non-empty. In other words, this side of the theorem, this assumption here implies that H is a subgroup of our group G. So we have 4 things to prove here. And let's do that. So since H is non-empty, there exists in X an element of H. The assumption, this here, implies that X times X inverse, which equals the identity, is an element of H. So we have the identity property. In general, any subset of a group inherits the associative law, so we have that for H. Since 1 and X are an element of H, and X can be any element in H, our assumption implies that 1 times X inverse, I'm talking about this assumption here, which equals X inverse, is an element of H. Thus, every element X in H has an inverse, and that inverse is in H. If X and Y are, to prove the last thing here, closure, if X and Y are elements of H, then X and Y inverse are in H. This Y inverse is because we just showed that the inverses are in H. Using the assumption, this assumption here, we have X times the inverse of Y inverse, which equals X times Y, is an element of H, and thus we've shown the closure property. So we've shown the theorem in both directions, and we have an equivalent way of showing that a subset of a group is a subgroup. On the next slide, I'll show you an easier way to prove that a subgroup is a subset, I should say, is a subgroup of a finite group. But in order to do that, we need an intermediate result, which I have on this slide. So if G is a finite group, and that's key here that it's finite, with element A, then a to the k equals 1 for some integer k greater than or equal to 1. So 1 here is the identity, and 1 here is just the integer 1. So consider this sequence: 1, the identity, I should say, a squared, a cubed. Since G is finite group and has finite number of elements, the terms in the above sequence cannot all be unique. So there must exist, in the very least, m and n, m greater than n, such that a to the m equals a to the n. Then using the laws of exponents, we have the identity equals a to the minus n, a to the n, that product. And then we have this here, so we just plug in m, a to the m. And then this is equal to a to the m minus n. And since m is greater than n, we can let this be our k, and that fulfills our theorem. So in the case of a finite group, a non-empty subset is a subgroup if it is closed under the binary operation of the group. So this is a fairly easy way to prove something is a subgroup, assuming that you're working with a finite group in the first place. So to prove this, we need to show that given closure, we have all the other properties for H, or a subset of G, in order to be a group. So first of all, H inherits associativity from G. I mentioned that in the previous proof, two slides back. That's always true. Any subset of a group is going to inherit the associativity property. Since H is not empty, it has at least one element, call it A. Since H is closed, all powers of A are in H. And then from Theorem 7 on the previous slide, there exists an integer k such that a to the k equals the identity. So we have the identity in our subset. So we have closure, we have associativity, and we have the identity. The last part is to show that for any h, small h, in our subset, that the inverse is also in H. So we know by Theorem 7 that there exists a positive integer, we'll call it n in this case, such that H to the n equals the identity. Since H is a group, since G is a group and H is also in G, we know that H inverse exists. We don't know that it's in H yet, but we know that H inverse exists. So multiply H inverse to both sides of this equation, and we get this here. So we have H inverse times H to the n, which equals H to the n minus 1. And multiplying it on this side, we get H inverse. And so H to the, because of the closure property, H to the n minus 1 is in H, and thus H inverse is in an element of H. So we've shown all four of well, we're given the closure property, but we showed the other three properties needed for a subset to be a group to hold true for H, and thus H is a subgroup of G. For a group G, an element A in G, the set of all powers of A is written as we've shown here. Let me point to that. And we define A to the 0 to be the identity, so that's by definition in this set. And since we're taking positive and negative powers of A, we also have inverses of the elements in this set here. Closure and associativity clearly hold true. So the set of all powers of A is a subgroup of G. In particular, the set of all powers of A is referred to as the cyclic subgroup of G generated by A. Now, it may not be all of G, but if it is all of G, as I'm writing down here, then we say that G is a cyclic group. In other words, the whole group is generated by powers of a given element. In this case, A is known as the generator of G. There could be more than one generator. And in fact, I have a theorem, which I'll get to in a second, that tells us which other elements are generators. We need a concept which you may or may not have seen before. It's called the GCD, the greatest common divisor of two integers. And I have an example here. So the greatest common divisor of 14 and 49 is 7, since that's the greatest integer that divides both of these numbers. So if G equals the set of all powers of A is a cyclic group of order n, then A to the k, where k is an integer, is a generator of G if and only if the GCD of n and k equals 1. In other words, n and k are relatively prime. And a proof of that is in this book by Rotman, which I've mentioned a few times, and I'll, as I say, put the link to this in the information to this video. Then we have another theorem. All cyclic groups are abelian, i.e. commutative. And we can prove that. Let A be a generator of G. So that's the definition, basically, of a cyclic group, that it has a generator, at least one. And take x and y and g. Then there exist integers m and n, such that x equals a to the m and y equals a to the n. Then using the exponentiation rules for groups, which we talked about earlier, x times y equals a to the m times a to the n, which equals a to the m plus n, and that equals a to the n times a to the m. In other words, it equals y times x. So we've shown commutativity here. We have the following very powerful and fundamental theorem of group theory, known as Lagrange's theorem. It says that if H is a subgroup of G, then the order of H, in other words, the number of elements in H, this symbol here, divides exactly the number of elements in G. So clearly this only applies to finite groups. The proof goes a little bit beyond what we've discussed so far, but I'll give you a link to where you can find the proof in a Wikipedia article. Then we have the following theorem that relies on Lagrange's theorem. All groups of prime order, in other words, groups with a prime number of elements, are cyclic groups. We can prove that here. Assume that G is our group of interest of prime order, so the order of G is P, where P is prime, and choose A, an element of G, such that A is not the identity, and let H be the subgroup generated by A. By Lagrange's theorem, the order of H is a divisor of G, and further, since we assumed A is not equal to the identity, there's at least two elements in H, the identity a to the 0, and then a to the 1. So it follows that the order of H is greater than 1. Further, since P is prime and H is greater than 1, and from Lagrange's theorem, the order of H needs to divide P, the only choice is that the order of H is P, and thus H is all of G, and that of course means that G is a cyclic group generated by A. Okay, so that's the last slide in this lesson. I have some more lessons on groups and rings and fields, and I'll follow up with those.